something, 2, 3, something like that. Our first speaker is going to be Andrea Viezzoli from Aarhus Geophysics, and he sees IP. I fear IP. Okay, this is going to change color.
Right. Oh, that's scary. Thank you. Thanks for allowing me to jump into this empty slot. I thought I would actually say something myself about IP instead of just commenting on the others. This work is partly funded by the INFACT project. There's a poster out there about the INFACT project, so I invite you to check out the website and the cool things we're doing there. Yeah, this was a bit of a joke that came out of workshop we had with USGS guys. You know, I tend to see IP everywhere, as you probably gathered by now. But I think there is a good reason for not ruling it out in many instances. So first start with some semantics. It's important, as I pointed out a couple of days ago, that we are very clear in the industry about this, you know, what this is. So IP, when people talk about IP, they usually refer to ground electrical methods. And we have to respect that and take that into consideration when we talk about airborne IP. The ground IP has been very useful in exploration. Then you actually have the physics. You know, induced polarization is a physical process associated with frequency-dependent resistivity. Then we have the airborne EM data, which in some cases calls for a frequency-dependent resistivity. Therefore, I think it's fair to call it airborne IP. As long as one realizes that it takes place at frequencies much higher than in the ground, therefore, it doesn't give exactly the same information about the subsurface than the ground IP does. So they are likely associated with different sources, at least partially. Therefore, I think it can be used as a complementary tool to ground IP, beside the fact that if you have it in your data and you don't deal with it, your resistivities will be wrong, which is a very good reason to worry about it. Another fundamental difference between ground and airborne IP is that in a ground IP server, you're charging the ground up here. In an airborne EM server, you're charging the ground up only whilst you're driving the current down. And that is a very significant difference. It has implications in terms of, you know, what type of frequencies we can actually excite, and why do different systems show different level or different IP signatures in the data space, depending on their waveforms. Now, this is a sort of a, you know, gospel plot when it comes to, you know, if you want to find an economical deposit, and I'm using ground IP, I hope to be somewhere here. Because somewhere here, this is where the tau constant of the cold model is higher. That's where the money sits. And we need to realize that airborne EM actually is exploring mainly here in this bandwidth. This is important. So what does airborne IP relate to in terms of geology, geochemistry, ground IP? I think the first two are still very much open questions. We need much more research. And this is a holistic effort. We need to work with geologists, mineralogists, geomorphologists to make sense of what is in the data, because there is no doubt that it is in the data. Just need to understand where it comes from and what use it has. But whatever the verdict might be, we can't ignore it. So a few key points on the physics. So it's been known for a long time that basically where you have something chargeable in the ground, you will have a contribution of IP currents that sum up with the contribution of the EM currents to give you what you actually measure. And basically this is the most important take-home message, that depending on how they interplay, what you see will change a lot. So at some stage, the contribution from the IP current can overcome that of the EM current, and the B field response changes sign. That's when you have the overall change of current from the total current, that's when the B field changes sign, not when the DBDT changes sign. That happens later. Anyway, then more recent work proved that the presence of resistive bedrock greatly enhances airborne IP. Airborne IP can't be just removed in the data space. It's impossible. You need to model it. And quite importantly as well, is that the moment you have IP effects in the data, your diffusion depth relationship of time versus depth ceases to hold. It's not valid anymore. So, just to show you the effect of layering. So we got 2 for responses here for a VTEM-like system. And this one here is a response of homogeneous half space without any chargeability. So 100 meters homogeneous half space, no chargeability. Then we put 300 millivolts volts, and you get this forward response here. Nothing goes negative, but you get the textbook type of example where you have a pull-up at the early times and a fast decay that Eswin was talking about at the later times. This is for a homogeneous half space. Then I'm going to whack a resistor below this chargeable layer. So the amount of chargeability in the ground doesn't change. Actually, it reduces a little bit. And this is what happens. So this is the response you get if you put a resistor below chargeable layer. The amount of chargeable stuff in the ground is the same. And obviously, this is wild. It's very negative. And yeah, your textbook type of a IP response. Very importantly, you can basically tell that all of this is IP, so which means that for the entire duration of a transient, you are gathering information only from the near surface. This doesn't always happen, so don't think that this is the take-home message, but in instances like these, you are sampling just basically that first layer, which may sound like bad news for some things. It's actually good news if what you care about is the near surface. All of a sudden, you have much more sensitivity to the near surface. And then I'm going to put a conductor at depth. So 3 layer now, nothing has changed in the chargeability. You just have a conductor at depth. And this is what happens. Double sign change. And this is basically the contribution of the EM fields from depth that finally managed to overcome the effect of the IP currents at surface. So if you think about depth, out here and up to there, basically you are mainly looking near surface, and then you just jump all of a sudden 400 meters and start getting information at depth. Of course, it's a bit more gradual than this, but just for you to image it in your head. And then, for reference, I'm going to take away the chargeability and just leave this kind of resistivity model to show you how this deep conductor, which may very well be the goal of your survey, would have looked like in absence of chargeability. It would look like that. So the only difference between these 2 for responses is that in here I've got 50 meters of chargeable stuff. And this is disturbing if you're an explorer, because you want these late time conductors. And if you don't deal with IP, you just take away the negatives, they're just gone. And if you try to fit any sort of tau decay, like some contractors do, you're going to get a very, very wrong answer. More on this. So these are just a couple of plots to show the interplay between the JEM, JIP contribution to the total magnetic field. And so this is what you measure in presence of a shallow chargeable layer. This is in B, this is in the BDT. This is what you would have measured in absence of chargeability. And this is just the polarization component. These are all negatives. And again, you can basically tell that in here, all you're seeing is basically the information from the IP, which again comes from surface. Now, this is about shallow chargeable layers, so you may think that this only applies to shallow chargeable layers. Actually, it doesn't, because if you bury the chargeable layer at depth below a resistor, it doesn't work below a conductor, but below a resistor, you're going to see exactly the same thing. But these processes will take place a little bit later in time. That's all. Something more about a deep conductor. This is quite illustrative, I think. So this is a 3-layer model. We've got a chargeable cover, resistive host, conductive basement. Now at this stage, the conductive basement is very deep. It's at 1,030 meters. This is actually thickness in there. So we buried very deep. And all you say in the measured data is the IP response basically coming from the surface. Then I'm going to take this conductive basement and bring it shallower and shallower. And you keep your eyes on these curves to see what happens. So this is just 100 meters shallower. They start changing. Of course, these guys never change because they just come from there. Then it changes again. And you can see the negative part of the transit steepening, getting steeper and steeper. Why is that? Because we have the effect of the conductors that are starting to do something to have that transit actually change sign again. And you get that. And then at about this depth, you have a measurable double sign change in there. We're at 500 meters with that conductor. And then you continue, and you get these type of curves that probably some of you have seen in airborne data. And in this case, it's not SPM. There's nothing wrong with the system. It's the combination of the information coming from here and the information coming from there. Okay, our approach to dealing with this is an holistic approach. In order to do good work on processing and inversion of IP data, you really need to have an holistic understanding of the entire process. You need to understand the geology. You need to understand the system's plausible responses, so run different types of for responses in different scenarios, different types of layering. You need to have knowledge of the possible pitfalls in a contractor's pre-processing, because that unfortunately tends to play a big role at late times, at low signal. Then you can have a preliminary assessment of the presence of spatial variability of, airborne IP in the data space. And then it takes careful visual inspection and painful manual editing of the data prior to the inversion. If you don't do that, in my experience, you can end up in a very wrong spot in the model space. Then we're doing this laterally spatially constrained inversion with ORS symbol, ORS workbench. As usual, and good practice in inversion applies prior knowledge, run a lot of realization. Got to be very careful in sampling the starting model space and the constraint space thoroughly, and assess the results both numerically and from a geological perspective. And if you're not satisfied, go back. And just pulling a line from Jared's, it's in airborne IP, it's even easier to turn a potential good into an ugly. It's fairly easy to do that, unfortunately. So, a couple of examples of contractors' post-processing related features that have been added to the data. So this is a sounding that has got IP, and then positive, negative. Now, there is no combination of layering that can explain this type of stuff. This is noise. The problem is that it doesn't look like noise because contractors are very keen in showing their signal clean, so they actually impose spatial coherence, gate by gate. So they only apply coherence in that direction, but not down the transit, and you end up with this. So it starts to be a fairly delicate call, where do I cut this data? Another example is this one. So this is over the same piece of ground, how an IP effect looked like in preliminary data delivery and in final data delivery. Yeah, it is problematic. So you also need a good discussion with the people in the offices, and have healthy discussion. What are you doing? Can I please get the raw data, kind of thing. As always, this is an example of a line of process data. That's the input data. That's the process data, the input to the inversion, and this is typical type of preparation for the inversion we've done manually. Okay, I'll take you to a couple of examples now. So this is from one of our INFECT reference sites. It's Cobre Las Cruces in Andalusia in Spain. The goal of the survey is to map the thickness of the conductive tertiary marls. They're conductive and they range anything from 0 to 200 meters. At the back at the bottom you have Paleozoic resistive rock. So the data contains IP. I don't have it here, but it does, both negatives and fast decays. So this is a resistivity that you get if you do not model IP. You just take the negatives out. That's a color scale down there. This is a data misfit associated to this result. And this is a known depth to resistive basement. And unsurprisingly, we are underestimating it, which is the typical thing that happens if you do not take IP into account, because you have that, pull up at the early times and then it comes down at the late times. You put a resistor over resistive stuff too close to surface. That's what it'll do. Then, if you model IP, this is resistivity you obtain. It actually matches the known depth to bedrock much better. The misfit decreases a lot, even though we're actually keeping more data. So that's plus. And this is a chargeability that we pull out. So these are the models. They're conductive and chargeable. And then you may ask yourself, why is they not chargeable here? Well, they are chargeable. We just don't have sensitivity to them because here it's too conductive. So in here, the contribution of the EM fields, the pure EM fields are too strong that we're not going to see the IP fields. So this is just lack of sensitivity. But up to here, to a depth of 20, 30, 40 meters, we actually pull it up very well. Now, as I told you, the aim of this was to produce a map of depth to bedrock from the geophysics. So we set to that goal, and so we produced a map of an frequency histogram of the spread of the resistivities that were intercepted by the drilling, by the elevation of a bedrock from the drilling. And we did that for the pure IP, for the pure EM case, and also for the IP case. Unsurprisingly, if you do not take IP into account, you see a larger spread of resistivities associated to the depth of the known bedrock, because IP will distort the transients in different ways depending on the thickness of the first layer. So you get a wider spread of possible resistivities to assign to your bedrock. If you actually do take IP into account, these are the spreads of the resistivities of the layers that intercept bedrock. So if you are to choose a representative value for predicting bedrock from resistivity, if you do it on the pure EM case, you will do something there, but you already know that you'll be wrong in a number of places because the spread is very high. If you do it on the IP corrected resistivities, you can pick something there and you will know that you'll be less wrong. And this map proves it. So this is a map of error in prediction of resistive basement depth in percentage for the non-IP modeled base resistivity and IP corrected resistivity. So if you do correct for resistivity, you actually get it wrong by 10 or 20% over vast portion of the area. Then because this is actually real, you get artifacts there and there. It's interesting that if you do not model IP, no matter which value resistivity you choose, you're always going to end up with something like this, with something which is wrong and it's not a DC offset, because it depends on how the IP distorts the fields, and that depends on the thickness of it. So you always end up with a gradient, an excessive gradient in your depth to bedrock that you pull out, and a gradient in the errors. This is an example from a kimberlite. I'll just jump to the most interesting bit. So we did resistivity, chargeability. This is all negatives. We're fitting nicely. This is an ISO volume, so resistivity and chargeability in there. Matches geology fairly well. The most interesting bit is that in this case, they actually had cores. So they measured IP on the cores, and they fit it with IP, with a call model. And these are the results they're getting from the cores. DO18 is in the top and DO27 is in the bottom. And compared against the call model parameters we pulled out of the airborne EM. And we actually are in the right ballpark. So the resistivities, we're probably overestimating a little bit resistivities in there, but the trend is correct. Chargeabilities should be in the order of hundreds, and we are there with this being more chargeable than that. C should be 0.6, 0.7. we're overestimating in here, underestimating there, but the trend again is correct. And the taus, quite surprisingly actually, we actually have them, the taus are there, so they should be in the order of 40 to 100 microseconds, and we're getting something in that order. So we're in the order of 100 microseconds, 180 to 100 microseconds. So, you know, we're looking at things from a very, very different volume and different ways of measuring, and it actually adds up. And this is, then we cluster the physical properties that we obtained, and this is a model of based on the clustering of the physical properties compared to known geology. So this sort of doesn't look too far from that, and this doesn't look too far from that either. So in here it says I'm done. Should I wrap it up, or do I have 5 minutes? Okay, that's good. This is another very interesting example. So we've got a lot of data in here. This is the sum of negatives in the SkyTem data. These are about 3,500 line cases that were processed with IP a couple of years ago. And so start with the misfit. Also Esmond had a very interesting map of misfits. So this is a misfit you get if you don't model IP. First of all, you got lots of gaps because there are too many negatives and you can't get a model out. But beside that, if you do model IP, your misfits go down a lot. A comment, of course, got to be very careful because in places we could be fitting with IP something which is actually 3D effects. So word of caution. It doesn't happen everywhere, but it's something that we should be aware of. This is a map of conductivity at 57 meters. This is what you would have gotten without modeling IP. This is the conductivity you get if you do model IP. And obviously this is something way more interpretable than that. First of all, because of amount of data, and also because you can actually join the geology in there, and there you're just left guessing. And this is a map of chargeability, two maps of chargeability, near surface and at depth, which actually shows there is some vertical dynamic in there. And one of my favorite, these are maps of taus. Now, what do they mean? I know the theory, you know, the higher the tau, the bigger the source of the particle of IP in theory. In practice, I really do not know. We need more work, but this is mapping geology somehow. And it's also a very, very stretched color scale. I mean, the difference between the blue and the pink in this there is probably like only 40% of the taus. It's not like we're spanning orders of magnitude. We keep the taus very tight. This is a cross-section across a known deposit. So these are lake bottom sediments, lick kind of things. They're chargeable. And this is, we have something chargeable at 200 meters, and this is the wireframe of the known mineralization from the area. If I've got time, I'll just show you this as well. This is from Lewis Pond, New South Wales. VTEM data, cross-section of chargeability compared with geology. So the mineralization is here. All this stuff around here are different types of alteration. And I think that with airborne IP, we actually are picking up alterations more than disseminations. But we need more fundamental research for that. This is also interesting because we have comparison with ground IP. So this is a slice of chargeability at 25-meter depth, obtained from the ground IP survey and inverted in 3D. And this is at the same depth, the chargeability you pull out of an SCI, of airborne IP, of VTEM data. And you can see some comparisons, and some things are different. Again, we're looking at things at different frequencies, which means that different sources, different processes, they do not have to overlap. This is where they're living in here. But when you go down, you go at 85 meters depth slice, then these things actually start comparing quite a bit more. And if you take a close-up, this is how they look like. And then for the fun of it, we try to take the IP out of the data. Basically, you invert, keeping IP into account, then take the chargeability out of the equation, forward it back just with the resistivity and see what it would have looked like, because we get those questions. And this is how this worth of data would have looked like in absence of IP. That's the original data. This is what it would look like. Don't do it. I don't think it's a good idea. Unless you're very stubborn and just wanted to look at voltages instead of anything. Because in order to get this, you already knew the answer of the corrected resistivity. So I'll wrap it up. Airborne IP is real and it's here to stay. What is it related to? Yeah, source is complementary to ground IP. It has very complex signatures in the data space. I invite you all not to jump to too quick conclusions without having studied the data space in detail. It requires a robust, holistic understanding of the entire process and care and preparation of the data prior to inversion. The sensitivity to near surface increases a lot, which to me offers great opportunities of integration with remote sensing beyond what we thought was possible. It has implications beyond the near surface, and we better worry about it, otherwise the resistivities will be wrong and we throw away useful information about the subsurface physical properties. Thank you.